Hi guys, my name is Michael Jung. You can call me Mike. I do have some professional experience with embedded systems and applied cryptography. And coming from Linux and looking for something more lightweight, I learned about NuttX and got fascinated by it sometime in 2017. And I've been playing around with it in my spare time ever since. Earlier this year, I decided to start my own business, planning to support my customers in the development of secure IoT systems using Apache NuttX and TrustedFirmware-M as two central building blocks. And today I want to share what I have learned so far from making these two play nicely together. Please be aware that I simplified on some technical details to hopefully make it easier to follow along. Now, as you probably have guessed, the motivation for integrating Apache NuttX and TrustedFirmware-M is to design better security into IoT devices. But what is IoT security? On a very abstract level, we might say that it is about establishing trust in a thing that it does what it is intended to do over its entire lifetime while operating in a non-trustworthy environment. Now, of course, we are all developing things that do what they were intended to do, but in this case, we are not talking about malfunctions or implementation bugs, but about an attacker trying to take unauthorized control over a thing. IoT security is all about establishing and maintaining trust that such potential attacks will not be successful. When talking about attacks, one has to distinguish between physical and logical attacks. For physical attack prevention, typically some form of protective housing is part of the thing, creating a security perimeter. If we think about an automated teller machine, the strong box that protects the cache would be that perimeter. In addition to making it hard to enter the security perimeter, many things integrate facilities that can detect unauthorized intrusion and will cause some emergency reaction. ATMs, for example, are occasionally equipped with a color cartridge which devaluates the banknotes by spraying them on intrusion detection. Naturally, physical security is not a topic for today, as it is mainly not a software topic. Things are logically attacked, on the other hand, via their external interfaces that cross the security perimeter without physical intrusion. This could be a remote attack via the internet, or it could be a local one via some of the device's external ports. It is known that ATMs, for example, have been caused to release banknotes by plugging USB memory sticks that have been prepared with some special autostart files. Logical attacks exploit security design weaknesses or implementation bugs. This is where TrustedFirmware-M can help. TrustedFirmware-M is a reference implementation of the Platform Security Architecture, PSA, which has been created by an industry consortium led by ARM. Let's have a look at PSA. The Platform Security Architecture is defined in a set of specifications. One of those describes the platform security model. It includes 10 so-called security goals, which are common to most IoT systems. Let's briefly cover those 10 goals. Unique identification. To interact with a particular device, a unique identity should be assigned to the device, and this identity should be attestable. This identity facilitates trusted interaction with the device, for example, exchanging data and managing the device. Security lifecycle. Devices should support a security lifecycle that depends upon software versions, runtime status, hardware configuration, status of debug ports, and the product lifecycle phase. Each security state of the security lifecycle should be attestable and may impact access to the device. Attestation. Attestation is the evidence of the device's properties, including the identity and lifecycle security state of the device. The device identification and attestation data should be part of a device verification process using a trusted third party. Secure boot. To ensure only authorized software can be executed on a device, secure boot and secure loading processes are required. Unauthorized boot code should be detected and prevented. Secure update. Secure updates are required in order to provide security or feature updates to the device. Only authentic and legitimate firmware should be updated on the device. Authentication at the time of download may be performed, however, the execution of the update must be authorized via secure boot. Anti-rollback. Preventing rollback to previous software versions is essential to ensure that previous versions of the code can't be reinstated, as this might reinstate security vulnerabilities. Isolation. Isolation aims to prevent one service from compromising other services. This is done by isolating trusted services from one another, from less trusted services, and from untrusted services. Interaction. Devices should support interaction over isolation boundaries to enable the isolated services to be functional. The interfaces must not allow the system to be compromised. It may be required to keep the data confidential. Interaction should be considered both within the device and between the device and the outside world. Secure storage. To prevent private data from being cloned or revealed outside the trusted service or device, it must be uniquely bound to them. Confidentiality and integrity of private data is typically achieved using keys which themselves need to be bound to the device and service. Cryptographic operations and trusted services. A minimum set of trusted services and cryptographic operations should be implemented as the building blocks of a trusted device. These should support critical functions including security lifecycle, isolation, secure storage, attestation, secure boot, secure loading, and binding of data. To implement the 10 security goals, PSA has defined the firmware framework for Cortex-M microcontrollers, which is defined in yet another PSA standard. It states that there shall be 2 isolated processing environments, one being called secure, the other one the non-secure processing environment. It does not specify how this isolation is to be enforced. A design based on 2 Cortex-M4 microcontrollers, which communicate via an SPI connection, for example, is perfectly reasonable. The non-secure processing environment contains the RTOS, NuttX in our case, and the application code, and it has direct access to most of the device's peripherals. In addition, it can take advantage of the services being provided by the secure processing environment via some form of remote procedure calls. In the secure processing environment, there is a simple RTOS-like executive called the Secure Partition Manager. It schedules the partitions which are conceptually similar to tasks and provides means for communicating between those and the non-secure processing environment. The partitions contain the so-called root of trust services. There is a set of services defined in PSA standards which are called the PSA root of trust services. Vendor-defined additional services can be implemented in application root of trust services. The number of partitions and their characteristics are declared in configuration files prior to build time. Some peripherals, typically the crypto accelerators, are assigned to specific partitions within the secure processing environment. Also, the root of trust secrets, which are typically cryptographic keys, are accessible only within the secure partition environment. The Secure Partition Manager might provide isolation between itself and the application root of trust service partitions, as well as isolations between those partitions, typically via the Cortex-M memory protection unit. This is dependent on the security level of the respective implementation. The well-defined functionality provided by the PSA root of trust services is made accessible to application code via the PSA Functional APIs. The corresponding PSA functional specifications define the respective C function prototypes and describe the provided functionality. There are 4 standard documents for cryptographic services, including key storage, attestation, secure storage services, and firmware update functionality. A separate certification scheme and framework is provided, which covers only the functional completeness and correctness of the implementation. This brings us back to TrustedFirmware-M, which is the reference implementation of the platform security architecture. TrustedFirmware-M source code is distributed under the BSD 3-clause license. The project is led by ARM, but silicon vendors also contribute to the project. As you would expect, the architecture picture of TrustedFirmware-M closely resembles the one from the PSA firmware framework. TrustedFirmware-M integrates MCU boot for secure boot and secure update, while the firmware update service is basically just a shim that translates between the PSA firmware update API and the MCU boot library code. As you can see, TrustedFirmware-M provides secure partitions for all the PSA services. The partition labeled platform on the right includes the entry point functions that are called from the non-secure processing environment, for which it serves as a communication gateway to the actual service partitions. Participating silicon vendors provide the hardware abstraction layer for their respective Cortex-M-based microcontroller, and this can include a device driver for the microcontroller-specific crypto accelerators. If not, then per default the crypto services rely on the software crypto library from the Mbed TLS project. A product vendor has to extend the hardware abstraction layer for his respective board, for example, to add support for a specific external SPI NOR flash chip used for firmware updates. And furthermore, a vendor might add application root of trust services. The isolation between the non-secure and the secure processing environment can either be enforced by using two separate ARMv6 or ARMv7M microcontrollers, or by exploiting trust zone technology, which was introduced with ARM version 8M. The most cost-effective way to implement the PSA firmware framework is with a single microcontroller that supports the trust zone extensions. So let's have a short overview of trust zone technology as defined in the ARMv8M architecture. This diagram shows various states latest Cortex-M microcontrollers can operate in. If you only consider one half of the diagram, you get pretty much the operating states supported by ARMv7 or ARMv6M processors. The processor is in handler mode whenever it is processing an exception handler, and it is in threat mode otherwise. And while in threat mode, the processor can run at the privileged or the unprivileged level, which is controlled via the npriv flag in the control register. If trust zone extensions are provided and enabled, then the processor can additionally be in either secure or non-secure state. Which security state is active at any point in time depends on the address of the machine instruction that is currently being executed. This means the contents of the program counter register R15. Or more correctly, it depends on whether this address is considered secure or non-secure. Simplified, one can say that the processor is in secure state as long as it is executing trusted code, and in non-secure state while it is executing untrusted code. Note that this makes security state changes very cheap. Branching between addresses of different security attribution change the security state of the processor as a side effect. And this is very cheap compared to the exception handling that is required to switch the processor from unprivileged into privileged level. I said that the security state of the processor depends on the security of the address it is fetching instructions from. But who decides whether an address is considered secure or non-secure? For this, Trust Zone introduces so-called attribution units, which mark ranges of addresses as either secure or non-secure. There are two major kinds of attribution units. One is the implementation-defined attribution unit, or EDAU, which from the processor's core's point of view is a black box that provides a security attribute when fed with an address. The EDAU's logic is outside of the processor core and defined by the silicon vendor. Typically, it's a relatively simple piece of combinatorial logic that derives the security state from a small number of address bits. The figure shown on this slide is from ST Microelectronics reference manual for the STM32U5 microcontroller, which is Trust Zone enabled. It shows the address ranges and corresponding security attributes as defined by the chip's EDAU. In the shown excerpt of the 4 GB address range, the yellow-brownish ranges are secure and the pink ones are non-secure. Note that the memories, both flash and SRAM, are aliased to both a non-secure as well as a secure address range. For example, the 2 MB flash is mapped to hex 8 million as well as to hex Charlie million. This means that the same code can be executed with the processor being in either secure or non-secure mode. Obviously, additional access control is required. We will get to this later. The second kind of attribution unit is the Security Attribution Unit, or SAU, which provides up to 8 address regions, each one defined by a base and a limit register with 32-byte granularity. Each defined address region is considered secure, Non-defined address regions are considered non-secure by the system attribution unit. The SAO-defined address ranges are overlaid to the ones defined by the EDAU. A given memory address is considered secure if it is attributed as such in either the EDAU or the SAO or in both. Certain registers are banked with regard to the security state of the processor. The most prominent example is probably the stack pointer register. There is both a secure and a non-secure instance of both the main stack pointer and the process stack pointer. This means that when untrusted code is calling secure code, for example, the stack is automatically switched to. The same applies to the control register, which holds the npriv flag. Those function calls between security states will automatically switch the respective privilege level. Furthermore, some facilities are duplicated. For example, there are two instances of the memory protection unit for the two security states. Thus, TrustedFirmware-M Secure Partition Manager can use the secure MPU to isolate the secure partitions from each other, while NuttX in protected mode uses the MPU to isolate the OS kernel from the user space application. The system tick timer is also replicated, which for example allows to implement independent schedulers in the non-secure and the secure processing environment. There are also two vector table base address registers, and those two independent exception vector tables can be defined for the two security states. Only a single instance of the nested vectored interrupt controller is provided, but it is trust zone aware. All interrupts can be configured to target the secure or the non-secure state. This means if a certain interrupt is configured to target the secure state, then the secure vector table will be used to determine the exception handler address and vice versa. System exceptions are either banked. This is the case, for example, for the system tick timer exception, since there are also two instances of the system timer. Or they always target the secure state, such as a secure fault handler or reset exceptions. Or they are configurable just as interrupts. The dashed lines in the figure show the possible state transitions due to exception entries or returns. Note that a non-secure exception can interrupt execution of secure code and vice versa. This also means that the NuttX scheduler can preempt a task that is currently executing in secure state. When this task is rescheduled at a later point in time, secure state is re-entered as a side effect of loading the exception return value into the program counter register. The solid lines show the function calls and returns as they can occur across security boundaries. The dotted line just shows the transition from privileged to unprivileged level by setting the npriv bit in the control register. By now we know that the processor is either in secure or non-secure state, depending on whether it is executing trusted or non-trusted code. In the AHB5 bus protocol, this state information is provided for every bus transaction via a distinct H non-sec bus signal. Trust zone aware components attached to the AHB bus matrix make use of this signal to enforce security. For example, a DMA controller might allow to set up secure DMA transactions only if the processor is currently in the secure state, which means if the H non-sec is deasserted during the respective bus transactions. A secure DMA transaction is one which deasserts the H non-sec during its own bus transaction. Peripherals that are not trust zone enabled require some adapter logic in order to attach to an AHB5 bus. For memory components such as flash and SRAM, this adapter logic would be provided by memory protection controller. Simple MPCs are configured via watermark registers. All addresses below the watermark are considered secure, and the ones above are as non-secure. If the MPC is targeted by a bus transaction while the H non-sec signal does not match the security attribute of the target address, then the transaction will be answered as write ignored read 0. If you recall that memories are typically aliased to both a secure and a non-secure address region, the MPC is the missing piece of access control that isolates trusted code from untrusted code. A peripheral protection controller is typically configured via a single bit. whether the peripheral belongs to the secure or the non-secure processing environment. If accessed with a non-matching H-non-sec signal, the transaction is once again processed as write ignored read 0. For non-trust zone-aware busmaster components, a master security controller defines whether AHB bus accesses from the busmaster should assert the H-non-sec signal or not. This concludes the short introduction to trust zone technology. Now that we have talked about the platform security architecture, trusted firmware-M, and trust zone technology, we can move on to the actual topic of the presentation, integrating Apache NuttX and trusted firmware-M. Trust zone technology has been designed to make the non-secure execution environment match the ARM v7m architecture as close as possible. Thus, as you will see, letting NuttX run in parallel to trusted firmware-M does not require substantial changes at all. Providing the PSA Functional APIs to NuttX application gets a little bit more involved. Let's first have a look at how the code is laid out in Flash in a typical implementation. The figure on this slide shows the layout for my STM32U5 based setup, which has a 2 MB microcontroller internal flash. In my setup, I'm distinguishing between firmware and application code. The idea is that firmware is developed and respective updates are provided by the device manufacturer. Applications for the respective device are developed and maintained by third-party system integrators with a toolchain provided by the device manufacturer. Let's look deeper into the firmware. Two artifacts are the result of the firmware build process. There is the 768 kilobyte firmware bin binary image that contains the functional firmware code. It is a concatenation of a trusted firmware-M image with the NuttX kernel image from a protected mode build. It is installed by programming it at a certain fixed offset into the flash memory. It's here at hex 40,000. The watermark of the flash's memory protection unit is configured in early boot stages such that the NuttX kernel and the application code are considered non-trusted code, while trusted firmware-M and everything below it is considered trusted code. The firmware bin image is signed with an RSA private key and the signature is copied into the image trailer. This image can be programmed during device manufacturing and it can also be distributed as a firmware update file that can be installed in the field. The second artifact is the 128 kilobyte BL2 bin file or image, which contains the second level bootloader code. BL2 is trusted firmware terminology. The MCU's ROM boot code is considered bootloader level 1, and the bootloader in Flash is considered bootloader level 2. The BL2 is basically an extended variant of MCU boot with support for the respective board. It contains the secure boot validation method for the functional firmware image. This means the corresponding RSA public key is linked into the BL2 image and used to validate the signature on the functional firmware image before booting it up. It also contains secure update functionality to update the functional firmware from an external SPI flash. The BL2 bin image is installed during manufacturing of the device, but this one cannot be updated in the field. STM32U5 specific security features protect the integrity of this image against potential attacks. The remaining flash areas in the trusted address range are used by PSA root of trust services as persistent storage. The non-volatile counters area, for example, is used to prevent firmware downgrades. It stores basically the last installed version of a firmware and can be used to only allow higher level firmware to be installed or updated. The one-time programmable area is used by attestation services to store device unique data like a serial number or a unique ID. And the ITS and PS areas are used as backing storage for the secure storage services. Minimal changes are required to make NuttX running in parallel to trusted firmware-M as long as you do not want to exploit the respective services. The basic system initialization is already done by TrustedFirmware-M code that runs before NuttX starts up. Thus, system clocks cannot be configured by NuttX. Up until now, I am doing fine with providing an empty STM32 board clock config function and configuring NuttX accordingly. All peripherals that are configured to belong to the secure processing environment will not be accessible to NuttX and must not be enabled in the NuttX configuration. Back when I started with the integration work, the exception common code for ARM v8M would load certain fixed exception return literals into the program counter register during exception returns, which breaks the case when a non-secure exception occurs while the processor is executing trusted code. But this problem was meanwhile resolved when the code to support lazy FPU register stacking was removed. Of course, you need to provide a matching linker script for the kernel build. TrustedFirmware-M starts the non-secure code by fetching the initial stack pointer and the initial program counter from the first two vector table entries, just as in the hardware reset case. And TFM expects the vector table to be at the beginning of the non-secure code image. And if I recall correctly, this is about all that needs to be done to have NuttX boot up and run besides TrustedFirmware-M. So let's look into what needs to be done to give access to the PSA Functional API for applications. Besides the actual TrustedFirmware-M binary image, the build process also produces the s_veneers.o object file, which provides the entry point addresses to 5 secure functions that non-secure code can call. Furthermore, the TrustedFirmware-M repository provides source code that is meant to be compiled into a static library and linked to the non-secure code. This source code implements the PSA Functional API based on 5 service functions that correspond to the 5 entry points in the s_veneers object file. All remote procedure calls from the non-secure execution environment to the root of trust services are tunneled through PSA connect, PSA call, and PSA close. Some shim logic must be provided to, for example, forward application calls to the PSA connect function to the TFM PSA connect veneer entry point, while maintaining multitasking consistency. What I mean by that is that if, for example, one NuttX task branches into trusted code and is then preempted by the NuttX scheduler before returning to non-trusted code, and the newly scheduled task is also branching into trusted code, this might cause problems. There are basically 2 options to handle that. The first option is to link the veneers object into the NuttX protected mode kernel build and to provide a character device, def TFM, with 5 IO control commands that call the corresponding secure function entry points in the veneers object. A static library meant to be linked to the user space code provides the corresponding 5 C functions, which will issue respective IO control commands on the def TFM device. The def TFM device driver enforces serialization by use of a mutex. That means only a single NuttX core task can call the secure processing environment at a time. This is relatively simple to implement, and this is what I have currently implemented in my setup. As a second option, the static library that provides the required 5 functions directly links to the s_veneers object file. That means that applications are calling into the non-secure execution environment without NuttX being in the path, which means that NuttX cannot enforce serialization. Instead, the NuttX scheduler must be extended to inform the TFM whenever it schedules a new task. It informs TFM via the TFM non-secure client extension load context function of the task switch. TFM will accordingly switch the execution context for calls from the non-secure execution environment. This approach provides lower latency and reduces lock contention, but is somewhat more complex to implement. Have a look at the non-secure client extension integration guide on TrustedFirmware.org for more details. With what has been described so far, the secure boot chain only guarantees the integrity of the firmware image, but not of the application image. Some extensions are required for NuttX to extend the integrity checks to cover all code running on the device. Furthermore, with the concept of shipping devices to third-party system integrators without any application code pre-installed, some facility for device management must be provided by the NuttX protected mode kernel image to enable initial installation and update of applications, for example, via a serial port or a USB port. NuttX is also currently not capable of running without a user space image. For example, the STM32 user space function is called in early initialization code to set up the user space BSS in data sequence. And there's also some code in the generic NX bring up that requires the user space image to be present. Changes are required here. Also, the integrity of the user space image must be guaranteed before any information from it is being processed. This requires addition to the NuttX initialization logic for application startup. The integrity check will include a signature verification, which needs access to the corresponding RSA public key, which itself must be injected in the PSA cryptography services key store by the third-party system integrator. My plan is to work on these topics over the next couple of months. Okay, this concludes my presentation. Thank you for your attention, and if you have questions, I'm happy to answer them.